So welcome to the seminar of the Sony Astani Department of Civil and Environmental Engineering. Today our speaker is John Riker Haymaker. John is a professor at Stanford University, and we are very honored to have him here as a guest speaker. Let me tell you a bit about John. John is an hybrid person. Let me tell you why. He is an engineer and an architect, or maybe an architect and an engineer. So he was educated at University of Michigan, Ann Arbor. He got his BS in architecture. Then he was at University of Illinois in Chicago, and he got a Master of Architecture. Then I went to MIT and obtained, that's very interesting, a S-March S, and he's going to explain to us what it is in design and computation. Then finally he went to Stanford, where he got his PhD in civil and environmental engineering. So not a usual cursus. So he's going to tell us about his plan, and I want simply to just, again, to welcome John here at USC. John, the floor is yours.
SMARC's Masters of Science in Architectural Studies, it's kind of a PhD light, where you go to MIT and get to spend a couple years and develop your own program. And so I was interested in things like artificial intelligence, computer science, and its intersection with architectural design. So I was out of the architecture program, but got to spend some time floating around and taking really interesting classes. So thanks for coming. Can I just get a sense of, are we all master's students here, PhD students? Who's a master's student? All PhD? Great. Any undergraduates? Okay, thank you. Well, welcome. So I'm going to talk about multidisciplinary performance-based design processes, and we'll explain that picture at the end of this presentation. So the problem that I'm trying to address with my work, with the research that I'll talk about today, is about underperforming performance-based design processes. Essentially, there's a series of metrics we might look at to evaluate a design process and understand, is it performing well or not. And when we look at, you can see a number of papers there that document our observations of current practice in industry, we find that stakeholders involved in the design process is fairly low. The objective definition, the way we actually define the objectives that we're setting out to solve in a design problem, are informal and incomplete, tend to generate very few alternatives. We tend to analyze them for very few relevant performance objectives. Our efficiency in doing this is very poor. We communicate our processes very inefficiently and ineffectively, and we communicate our decision rationale. Once we actually go through this design process, come up with a design decision, our rationale is very informal and inefficient. I'll give you some specific examples of why I argue that, but this is the problem I'm trying to address. The theory is, if you improve the processes, if you do better with your design processes, you're going to end up with a better product, a better design. So I'm going to just quickly, so you get a sense of where I'm coming from, give you a little bit of my background of stuff I was up to before I went to Stanford. Then I'll go through my research, and I'm going to talk about essentially 5 methods, tools and methods that we're developing to address some of those problems I just talked about. PIP, process communication, design scenarios, requirements-driven parametric modeling. PIDO is design automation and optimization. MacDaddy for decision communication, and DEAM for assessing and comparing design exploration. I'll also quickly talk about some of the classes I've been teaching at Stanford that's related to these issues. So before I decided to actually go do that degree at MIT that I talked about, which was a PhD light, I spent some time in practice as an architect. I worked on Navy Pier in Chicago, had a chance to work on Disney Concert Hall here for Mortensen on the contractor side, done some of my own hacking with a bandsaw and table saw and things to do my own renovations, and I also worked a bit on the San Francisco International Airport. I guess one of the reasons I bring this up was I was a owner's representative here. I represented the construction interests in the Disney Concert Hall. I was an architect there, so I've sort of seen the industry from a number of different perspectives. So I got really turned on by the computer as a potential design exploration tool in my thesis at University of Illinois Chicago. This was a generative algorithm called Misbeast. It was formulating and then mutating the rules of Mies van der Rohe. And so the idea here was that they had international style architecture, which was sort of being plunked down through cities everywhere. This would be a generative algorithm which would mutate those forms to be more site-specific, problem-specific. I went to MIT with this idea. That first slide was just about generation. I started to be interested in how we could use a computer to actually test these forms that we're starting to generate. So in this case, this was something called filter mediated design, a series of agents in a virtual collaborative environment which would look at a shared design space and evaluate for things like enclosure or light or structure or space. And then there were some negotiation protocols that would help these different agents to communicate and to negotiate over the design to find designs that would satisfy all these criteria. I then went to the Disney Concert Hall and had the opportunity to build 4D models. People familiar with 4D model here? Essentially the idea is connect the geometry to the construction schedule to help you visualize the construction process and find bugs in your construction schedule. So this was, I found a fairly transformative process for me because it wasn't just about taking one geometry, but in fact bringing geometry from the architects, from the subcontractors, from the sub-consultants. There are actually about more than 13 different models I need to bring together to create this one view of the Disney Concert Hall and then create the construction schedule to help it play it out. I didn't bring the animation with me, but we could basically watch the Disney Concert Hall built from the ground up. Here are the different construction activities, and the color helps you understand what's going on in terms of the different activities. So here we have a erect enclosure scaffold. So that's what we're doing right here, is we're erecting the scaffold to build the enclosure right there, for example. And then went back up to Stanford to do my PhD, which was motivated by my experiences on the Disney Concert Hall. And I formulated what I call the perspective approach, which is essentially, for those of you who are deeply involved in BIM, there's, I think it's breaking down now, but there's been a perception that there's sort of the BIM model, a integrated model of the entire project in a database that every kind of buddy builds and adds to. My experience is these processes are much more distributed and dispersed than that. You have architects, you have contractors, you have everybody with their own view and their own models. And the real challenge is how to connect and relate those models and keep them up to date and integrated. And so that was the problem that I attacked here. We had a problem at Disney Concert Hall where Frank Gehry would build, model of the concrete slabs here, and then the steel detailer would build models of the steel members which would form the frame of the building, and then some hapless soul, in this case this was one of my jobs at the Disney Concert Hall, was to design these things called deck attachments which would help you connect the steel beams to the concrete slabs. And unfortunately in a Frank Gehry building, nothing, if it's a perfectly orthogonal building, you don't really have an issue. The slab sits right on top of the beam. But with all these different forms and angles and things in the Disney Concert Hall, there were lots and lots of these deck attachment conditions. And as the architect was changing their concrete slabs or the fabricator was changing their steel beams, these deck attachments were constantly emerging as necessary conditions or going away. So I formulated this process of building a dependent perspective called deck attachments from steel framing to concrete slabs. I actually did that by constructing a series of sub-geometric models that were all dependent on each other. So first taking the beams and decomposing them in terms of edges, slabs, decomposing them in terms of bottom faces. I won't go into detail here, but this is about locating those different conditions where the deck attachments are needed, and then actually generating each deck attachment. So I found I could, with some fairly simple geometric transformations, create a graph of transformations that would get me from beams and slabs to deck attachments. Anytime I changed the beams or slabs, I'd get deck attachments. I built a piece of software that allowed you to easily connect together these different models and then control their integration as things changed. So that was my PhD thesis. and then I began as an assistant professor at Stanford. Okay, so the work I'm going to present to you now is, as I'm learning as an assistant professor, it's not my work, it's your guys' work, the PhD students' work. I've tried to assemble a multidisciplinary team that really addresses this issue of multidisciplinary integration of design. So you can see I have folks from management science and computer science, really decision experts, some architects, some structural engineers, some mathematicians, some mechanical engineers, all working on different aspects. And I'll explain these different projects and what they've been working on now. So the first project I want to talk about is something called PIP, or Process Integration Platform. It's work that's been funded by ARUP as well as SCIFE, or the Center for Integrated Facility Engineering up at Stanford. So the problem that we're addressing, I'm not sure if you guys have seen this curve. It generates some dispute amongst folks, but it's essentially saying that productivity in the construction industry is actually decreasing, while in other non-farm industries it's rapidly increasing. They're inefficient. We've probably all seen the NIST report that says we lose a lot of value due to interoperability problems, and it's ineffective. We're kind of constantly missing the target. A lot of our LEED buildings are actually performing worse than buildings that are not LEED certified.
What is non-farm? Sorry,
No problem. Non-farm meaning everything from mechanical engineering, airplanes, development and building of airplanes, industrial uses, basically everything that's not construction and that's not farm.
Okay, so you remove agriculture.
That's right. So I'm going to go through some observations that Reed and I did, in this case on a project by Ove Arup. So here's a decision matrix that was built, and the argument here is that project teams are struggling to collaborate. They're struggling to bring together all this information to make good, efficient, and effective decisions. So they built this decision matrix, and here they were looking at essentially the different goals that they were trying to achieve and different HVAC options that they might use to achieve those goals. They came up with some sort of rating system, and they actually found that displacement ventilation turned out to be the lowest score. But when you actually got to the design solution that was proposed to the owner, we saw that displacement ventilation was actually something that was proposed throughout much of the building. And the point there being that essentially either something happened, I'm sorry, getting out of whack here, either something happened here that made them change their mind, but they never updated their information, or they never actually got this analysis into the actual decision-making process. So teams are having trouble just getting their information together and present it in the right format to make the right decisions. Teams also struggle to share processes. So that's about sharing, the first one was about sharing information within a project. This is about sharing processes across projects. So in this case, the actual process was that the client asked for information about the embodied energy in different structural materials. They wanted to make a good sustainable choice about whether it should be steel or concrete, for example. So the designer had a Revit model and went about trying to find out, how do I find out about the embodied energy in these different materials? Asked the forum, the Arab forum, his colleagues, searched the internet for some sort of process, couldn't find one. So when it came time to make a decision about steel versus concrete, they had to go with no information. They just had to make a call. They couldn't find a good process to get LCA information out of a model. Turns out that there were these processes existed. It existed in Australia, and it actually existed in my lab at the time, where we were exploring a model-based life cycle assessment tool called LCA Design, which is being developed out of Australia, where you build a Revit model, you export an IFC model, you link it with some tags and to an LCA database, and you get embodied energy information. So the process was out there, it was in the world, could have been applied on this project, but the designer wasn't able to access this process and execute it on their project. Project teams struggle to share processes. Finally, firms struggle to understand processes. In this case, there is this process of exporting from a Revit architecture model, going through quite a complex geometric transformation process to get the tool, to get the geometry, excuse me, into a good format in which we could use the Radiance daylighting software to understand and create daylighting videos that would help us understand how the different window configurations would perform in terms of daylight. It turns out that Arup executes this process with this manual geometric transformation over and over and over again in their, between their 10,000 employees around the world. But the management has no way to sort of step back and understand what processes are going on all these individual projects. Which ones should they be investing in, trying to improve? They have no transparency into what's going on in these individual projects. So, really see three opportunities to improve that curve I just said, to improve our efficiency and effectiveness on processes. We want to be able to collaborate better within projects. We want to be able to share our processes across projects. We want to be able to understand our processes across an industry. And all of these, at least our hypothesis involves better communication of design process. So how can these design processes be communicated better? There's this idea of an information processing view of the firm. Design is just an information processing activity where we start with some sort of goals and objectives. We have people who create information. They create this information based on other people's information, and it's ultimately just a big information processing exercise. So with that view, to get us to buildings, we think we can come up with something. And the criteria here is that we're particularly dealing with complex design processes. Move on. Okay, so the big idea here is today, and the way that sort of information management systems have evolved, they're hierarchical. On projects today, we often use FTP sites, even SharePoint sites, which tend to organize their information hierarchically in these sorts of data structures. But we don't actually process information like this on a firm. We don't do our work, pass it up to our CEO, have our CEO process it back down to somebody else who's going to do the work. We're living in a network society today where we're connecting in a network way. So how do we tend to organize our information on these projects? We're still doing these hierarchies. So the intuition is that we want to start to organize our information in these process flows. So how do we go about doing that? Basically looking at three research fields. And those are organizational science, human-computer interaction, and process modeling, in order to develop what we're calling a design process communication methodology, understanding what it is that we have to communicate about design processes. And we've found, I think I might have a slide on this in a moment, but that essentially literature is telling us that we need some sort of environment that's very social, shared, personalized, usable, embedded, computable, distributed, modular, transparent, and scalable. I don't have time to go into definitions for all of those, but we've essentially defined a series of criteria which are going to help us define a design process communication methodology and tool. So this is just a bit of an example of some of the characteristics, like for example for shared, the ability to search processes via passive information exchanges. These are things that we found in literature that different people have said. We've aggregated these criteria and are going to develop a system to fulfill that. That's just a high-level view of PIP, and I'll go into an example of how it works. But essentially, you do have your hierarchical view of information, but you also have this networked view where you're connecting information together. And each of these nodes in PIP will actually connect to an actual, say, SketchUp model or a Ecotech lighting model, for example. So just walk through an example of how PIP is working. So here, this is how we're tackling collaboration. That you might start a project that, you have architecture and daylighting analysis. Well, we're going to draw a dependency between architecture and daylighting analysis. And we might say, okay, now we want to do some energy analysis. So we'll draw those dependencies as well. Click on energy analysis, and we'll open up into a sub-process in which we're talking about coming from the architecture model and the architecture folder into a daylighting analysis. Then we might want to do an energy analysis, which needs to pull on the geometry, but as well as the daylighting information to know when you want to turn on and off the heating, ventilation, air conditioning system. and ultimately some decision matrix. If we upload a file into pip, we'll see that items downstream need to change. So we're starting to understand how this information is impacting connected and related information. And so this is allowing the whole team to come together. You can see different people attached to these different folders to come together in this virtual web environment to start connecting their information together and control their analyses. Okay, so what about the sharing idea? Well, we're building a sharing interface into pip where we can search. We can just search for anything, or we can search based on dependencies. So here we're searching for a process that has input of an architectural IFC file and output of lifecycle assessment. And this process here shows up as well as other processes that might fulfill those criteria. We can then copy that process, paste it into our own project, and modify it to meet our needs. Finally, understanding, we're building in methods to comment threads, metrics about process usage, how long does it tend to execute this process, how many times do people tend to iterate with the process, et cetera, to help us understand overall how different processes are being used and shared. I just explained all that. Okay, so we built that platform. That gives you a general sense of how it works. We're using it in classes. So we'll bring together, in this case, 32 students on 8 design teams representing a number of different design roles. We pair them with industry mentors to give them real industry problems. And their job is to analyze and design at least 2 design alternatives for a multidisciplinary set of criteria. And we're starting to develop some, this was just data that we just did this last winter quarter and are starting to assess the data. So I pasted these in fairly quickly, but so here we have different projects that you can see. So some people working on, say, Doyle Drive up in San Francisco, the bridge or the tunnel, Stanford Graduate School of Business, a Hong Kong rail station, high-speed rail, Mariposa in Fresno. These are 3 Fresno train station potential locations, and ultimately a developer in Arizona for a housing complex. And so what we can just see here by looking at this view to help you understand is we're mapping the, by color code, who is connecting to who. So these are different designers on the project. And so we can see that, for example, this person is connecting a lot to themselves and somewhat to others. So obviously a lot of people are connecting to their own models a fair amount. But you can see that overall this project has a fair amount of integration. People are connecting their models together more, whereas as we get down here, this shows a little bit less integration. So these arrows are helping us just assess somewhat qualitatively, but how integrated their design process is. So that just gives you one example where if you were to look at this particular person, Smith to Ramirez, and look at their connections, you can find in pip by using the search which process they connected. And interestingly, so if we look at this graph now based on the grades in the project, who performed a better analysis, who came up with a better design process, we're finding there is some pretty interesting correlation between those who did more overall integration on the project and the higher scores versus those who did less integration tended to get less scores, less high grades. And this is also showing something else which is sort of interesting. We had these 3 high-speed rail projects, and we could start to pick up where they were starting to connect information between their projects. So somebody, say, on the high-speed rail in your location had some models that somebody in the Mariposa project found interesting and useful.
Excuse me.
Yes?
The high-speed rail was the design team of the 8 segments of the California Rail, or was it a different project?
No, this is the this is VBN Architects up in the Bay Area, which have, forgive me, I don't know how the segments are exactly broken up, but they have this sort of Bakersfield and Fresno area, that region, and they're doing just station design. Yep. And we can also start to look on this information now that we're starting to draw these dependencies between different models. We could start to see where there's a lot of common information flows. So for example, the darker green means there are more arrows being drawn. We can see lots of people are taking Revit and making images out of them, whereas essentially not many people are taking Revit and connecting it directly to an MS Word file, or in this case, even to an Ecotech file, which is sort of interesting. Right on. So then we can also start to understand, we can start to query this data and understand based on the time of dependent models when they've been uploaded that, for example, here it was just about a 2-minute difference between building this model and exporting an IFC file, whereas in other cases, let's see, that the time might be much more, so we can start to understand these processes where the time is being spent. Okay, so I think I'll, yeah, so for example here we can see it's common and time consuming. The size of the arrow is how common, the depth of the color means how time consuming, and so we can see that it's fairly time consuming and common to use an AutoCAD file to create a Revit model. So we're often, getting the AutoCAD drawings from those who are not yet BIM oriented and needing to recreate these things in terms of Revit files. So the big idea here is to go away from knowledge management, which is essentially we're using directories and email to mail our information around, moving more towards social networks, project pages, discussion forums. So at the moment, we kind of throw it over the wall. There's not a direct link between the way we store and pass information around and how we actually try to manage knowledge on these projects. So here we're going into more of a network view where the knowledge management is kind of emerging from our just use of this system. Okay, so that's PIP. I might just take a quick breath there. That was a whirlwind.
Curious, maybe I was paying attention, but you look at how you can scale these interactions in terms of number of interactions. I mean, if the project gets bigger and bigger and bigger,
Yep.
each project,
Yep.
what would be the tendency, the trends with this huge project?
It's a great question. I mean, the intuition is that as projects become bigger and bigger, the need for something like this will increase, the ability to understand where your information fits in the context of this very large project. We haven't tested it. That's certainly the next thing. We want to take PIP and we've built it and tested it in the classroom so far. Next step is to take it out onto real era projects. And
I would expect that if you have n objects, the interaction between n objects would square as n squared.
Yeah, I don't think that's quite right, but it's fair to say that the complexity will raise. And then how do you manage that? Well, how are we managing that today? You have those interactions and connections, whether you're trying to model them in the computer or not. So we have to manage them somehow. The intuition, what we're testing here is, can we represent them in the computer, and how useful is that? And that's a great question, is do we get to some point of diminishing returns where the complexity becomes so great that we're better off using our brains to try to manage all of this than computers. Okay, so the next problem here is, next tool is design scenarios. It's called requirements-driven parametric modeling. Any parametric modelers in the audience out there? Anybody use Digital Project or even Revit a little bit? Some Digital Project? Okay. Hopefully this will resonate with you. So here, Victor Gane, has been working for a number of years with architect SOM and has come back to do a PhD. And one of his first tasks was to go back out and do a survey of leading high-rise design firms. There were about 6 or 7 firms who were involved in this survey. And this just kind of reinforces the information I gave you at the very beginning, that we found that for when they're designing high-rises, the way that they define their goals is not very clear. They tend to generate very few options, really only about 2 or 3 that they'll actually build a model of and do any kind of analysis. The analyses that they're doing are things like aesthetics, area efficiency, maybe a little bit of structure, site views, budget, But you can see that in conceptual design, they're not really considering things like energy, thermal, daylight, some of those things which we might consider sustainability criteria. They tend to only get to those later in design development when the real form of the building has been made. And so then, yes, sir?
I had a question about you put the interaction between architecture and HVAC. So one direction.
Yeah.
What is the feedback? There's a lot
Great.
of energy. Feedback from HVAC to the architecture.
It's a great question. So there's a simplification that we've done, which is to model this as a directed graph. You know, you're going to start with sort of partial, no information, something about goals, and you ultimately want to get to a building. Lots and lots of iteration. You're going to get there, you're going to do your HVAC, you're going to be like, holy smokes, those windows are way too big. Look at how big this HVAC is, we need to go back and change. Now you can, and we've experimented with it, you know, modeling those iterations and those loops. And we'll often do it, but to JP's point, there's increased complexity every time you draw one of these arrows. So what we're experimenting with here is model the directed path. And then we have this idea of, you saw the greens and the reds? We can support iteration in that way. So that if I go down, I find my HVAC is really inefficient, I can go back up to my architecture, I can change my architecture, my HVAC's going to go red, now I need to go back down to the HVAC, remodify the HVAC. So we'll support that iteration in that way.
But it might be also sustainable building and green building has to do something with it too. So as far as the materials, as far as if you're trying to have green, usually green exterior.
Yeah.
Has the right, everything is considered actually.
Sustainable design is all about these interconnections. The world, yeah, it's all about these interconnections. And so we're looking for that sweet spot of how to model all those interconnections. And should we model all of them, or can we model them as just a directed graph and then manage those connections through status? Okay, so very few alternatives, very few analyses, lots and lots of time. Architects are spending for about 5 weeks, mainly architects, not a lot of mechanical engineer, structural engineer involvement. So I'm going to walk quickly through a couple of case studies that Victor did in terms of trying to implement what's this technology called parametric design into the design of high-rise. So I'm going to look at two. I'm going to look at what's viewed as a somewhat successful application of parametric CAD on the Infiniti Tower in Dubai, and then a somewhat less successful implementation, Transbay Tower in San Francisco. And I'll hopefully explain why they were viewed as successful and unsuccessful. Infiniti Tower, it was a competition. It took about 2 weeks to execute a residential tower, 3 architects, and a fairly well-defined set of requirements went into the project. Essentially, you could see the ocean and the city, the 2 main views, are in the kind of narrow part of the project, whereas the way the building is going to sit, the main views are going to be looking at adjacent buildings. It's not an ideal site, but that was the site they were given. So this is the base of the parametric model. So essentially what we're doing here is we're connecting geometric elements together and then being able to access that model with parameters. So the main parameter driving this is building twist. We can set different building twists, and then the building will twist, and all the things like the floors and all the elements are connected, so they'll follow along. So right now this is just the overall skin, and you can see it's moving kind of quickly. There are the floors. But we're doing things like changing this angle and then changing the radius. Start to add more detail to that parametric model, so starting to lay columns around the external, extruding up those columns. Not sure why this slide isn't dancing as well, but then ultimately looking at just a particular floor slab and adding great detail about how the columns go together. So there we go. So here we're manipulating parameters like column spacing, spandrel beam depth, slab depth, to be able to look at this whole possible solution space of designs. And ultimately looking at some constructability issues, such as the way we define the columns allowed us to look at different configurations of columns, where here we have this completely sloping and twisting 2 degrees of rotation column. Here is a bit of a hybrid where it's sloping in one way but stepping, and then this is what we ended up calling the Thunderbolt, which is essentially a a connection which made rebar and things much more easier to frame. And that was the end result. We were able to feed the parametric model into structural analysis to support finite element analysis, as well as into digital prototyping to allow wind tunnel testing and visualizations to help us understand how this thing would look. And it's under construction now and winning lots of awards. So the real key there was that there were a fairly well-defined set of requirements that Victor, as he was building this parametric model, could react to and build a parametric model which would help address those comments. I guess one thing I didn't mention, one of the big goals of this twisting tower was, I showed you at the beginning that the site was sort of long and narrow. This allowed you, as you got the higher floors, to twist the wider part of the building to be able to take advantage of the views. Also discovered there were some structural benefits to that. The twisting helped to deflect wind, as well as create a little bit of a damping motion in the structure. Okay, Transbay Tower, larger project, more people involved, and the requirements were really just about square footage. There wasn't really much else about performance or what this building was really trying to address. I'm going to kind of not spend a lot of time on this case study, but just jump to the point. Victor, poor Victor, had to spend a lot of time, and he built from the ground up 6 different parametric models as he was constantly reacting to the design team as they started to kind of discover requirements, express requirements to Victor. And this model ended up not being used in any analyses and was considered, while somewhat useful, not as useful a use of parametric modeling as the first case I told you. So the real question here is, can we avoid a lot of this time investment and actually hone in on really good designs if we better define these requirements from the beginning? So the point is that all this stuff is connected, and is if you sort of start to break something in a parametric model, everything falls down. So we're developing a system called design scenarios. It's a collaborative design space definition and exploration, essentially a formal process of developing a requirements model, creating what we'll call a design scenarios model. I'll explain that in a moment. Creating what we call a parametric process model. From that, we can actually develop our parametric model that's dependent on the requirements and a sort of systematic process for understanding what our parameters and relationships need to be. We'll then pass that parametric model into model-based analyses and then come up and explicitly analyze the options in terms of the requirements. Here you can see we're starting to model some of those iterations with our arrows and things. So the design scenario model involves taking the design team through an explicit process of starting with requirements and then decomposing those requirements into actions. How are you going to achieve that goal or constraint? Strategies. Sometimes you break those actions down into more detail to talk about how you're going to do that. Then we define parameters and constraints on those parameters. So the model starts to look like something like this, where we know that we need to have a buildable area setback. So we're going to need a property line in our parametric model, and we're going to need some sort of setback. And so here we have a parameter defined setback and a parameter called radius. These models can get quite complicated, but the process of going through this explicit rationale of defining, getting from requirements to parameters, helps the designer really think about how they want to set up this parametric model. The next step is then to go into a parametric process model where we take those parameters and constraints and we start to define the geometric relationships between the parameters and constraints and components in our parametric model. So this would take me too long to sort of explain the rationale in here to you, but you get the general idea that we start to develop a language for describing these geometric relationships and constraints. And then the idea is you can then use this graph to understand, okay, well, what if we modify, in this case, this is the building width, if we move it from 40 feet to 70 feet, this graph then helps us understand what other components in the model are going to be affected, in this case, quite a few. Okay, so that's getting from essentially requirements to a design space. How do we get from a set of requirements to a well-targeted space of designs that we want to explore? Now, how do we really suddenly we can generate thousands of designs. How do we actually analyze these? You guys want to sit down, or you all right? Do you want to sit down, or okay? So this is work called PIDO, or Process Integration Design Optimization. Forrest Flager, Ben Welly, Akshay Ada I should have up there as well, and myself have been working on, funded by a number of people, as you can see. So here the problem is a lot of management time and very low iteration in our design exploration. So this was a survey of Arab engineers, and we asked them essentially, how much time are you spending specifying your design process, executing your design process, managing your design process, and reasoning about the results. And we discovered that they spend very little time sort of setting up and specifying what they're going to do, spend about a third of their time doing what they really view as a value added, generating an analysis, spending more than half their time managing information, just maybe building a new CAD model out of a drawing, looking for the right sets of information, and they're spending relatively little time reasoning about their models. It's taking them about 7 weeks sometimes to set up and run an initial analysis, and then they get some economies just because they've set up a structure, and it takes them about 5 weeks to do another set of analysis. So they're really only getting through about 2 iterations in a design process, in a conceptual design process, not really systematically looking through the whole solution space. So we went to aerospace and mechanical engineering, and they've had this problem, and asked them how it is that they're addressing it, and they've been developing something called Process Integration Design Optimization, or PIDO. And so I'm going to explain PIDO in the context of an initial case study that we did on a simple classroom problem. So here we're going to parameterize this design space in terms of series of design variables. We can do different building orientations. We can do different building lengths. We can create different window-to-wall ratios, bigger windows, smaller windows, and we can look at different structural steel sections on this frame. We're going to constrain this a little bit. We're going to say we're only going to look at one particular floor area. So as we make our building longer, it's going to become a little bit narrower. I think it was 960 square feet. We're going to constrain it for structural safety. All designs have to meet minimum structural code, or else they're not viable. And we're going to constrain for daylighting performance. We need a certain amount of daylight in the space for it to be viable. And we're going to set some objectives on this search. We want to minimize the first cost, and we want to minimize life cycle operating costs. And these are often things, first cost, life cycle costs, that we need to trade off. This is the platform for process integration design optimization. So here you can see digital project feeding into Energy Plus, also feeding into an FEA processor, preprocessor, structural steel section database. GSA is the AirUp version of ETABS for doing structural analysis, a building code check, and an optimizer. And we start to get some pretty interesting results that help us to understand this design solution space. So we're no longer looking at individual point designs, but understanding what the space of solutions are. So this is just a structural engineering view. And here we're seeing that these are different beam section types and total cost. And so we can see that there are 2 beam section types which are leading to the cheapest cost. It's good information for a designer to kind of understand, to know where the general beam section types are that lead to best designs. It's called a parallel coordinates plot. Each blue line, or each line, excuse me, represents an individual design. So we can go here, this is cost, and so assuming we want to minimize cost, we can follow these blue lines along and understand which other parameters are leading to the cheapest cost. So we can see that there are sort of a couple longer building lengths which are leading to the cheapest cost. Reason for that is as the building gets longer, it gets narrower, and the span is going in the narrow direction, so we're getting lower spans which are leading to lower structural costs. You can see a whole segment of girder sections which lead to good designs. Columns essentially pick it. Doesn't matter what column you use, it's not going to impact cost very much. And here are those 2 beam section types. So you can start to, as you start to use this PIDO to generate this whole solution space, you can start to get some really useful and interesting information that can feed designers. So this is just a pure energy view. So here we're looking at different building orientations, different building lengths, and a surface plot, which is showing sort of the overall performance of the space. So you can see here, for this orientation, that's where the best designs seem to exist, although there are a couple other orientations here where there are slightly better designs too. An interesting surprise emerged from this, which was this was a building, we sited it in San Diego. And as it turns out, the building geometry that led to the most efficient energy cost was one with huge west-facing glazing. And, you know, sort of made my building science education brain sort of explode a little bit. I'm like, wait, west-facing glazing, no, that's bad. They taught me that first day of class, right? Big heat load, got to do a lot to keep that space cool because the sun's going to be pounding in there in the late afternoon. Well, when you step back and look at the way we set up the problem, this is a classroom. The occupancy is out of that room by 3 o'clock in the afternoon. Space can get as hot as it wants to after that. So that's okay, but we're getting great daylighting potential through the rest of the day because of this big glazing. So just, you know, it sort of gives you a sense. These models don't necessarily pop out the right answer, but they give you a lot of good information to start to query the problem and start to understand where some good solutions might lie. And then here we're looking at just a trade-off. So each dot represents a design. The gray ones are ones that violated constraints, either the structural constraint or the daylight constraint. And then we can see that we have a Pareto front here looking at the trade-off between basically first cost and life cycle cost. Are you really adverse to first cost? Well, then you're going to want, you know, one of these designs along in here, but you're going to have to sacrifice something on life cycle cost. Okay, so Forrest Flager has taken this work on to look at actually out into industry to apply it on stadium design. So here this is looking at structural section size optimization. So we're not modifying any geometry here. We're essentially just plugging in and out different beam types. And he found that in the traditional practice, we first followed that, and they were able to do something around in the order of, let's see, 42 iterations. Let's see, 39, excuse me, iterations. And it took them about 14,000 seconds per iteration and achieved a metric tons of 14 metric tons of steel weight. Going through a optimization process that was serial, in this case just one computer, one processor, we were able to essentially speed up the process by 42, each cycle taking 345 seconds, and we were able to drop the steel weight to 1146 metric tons, which was about $10 million in savings. We've then put that into a parallel computing environment, high-performance computing environment, where we showed that we can significantly speed up the factor even more, to the point where it seems possible to set up an experiment like this, say, in the morning, go out to lunch with the design team, come back in the afternoon, and get results back right away. Here, just another example on another stadium roof, where we're able to achieve approximately the same type of savings. So the message here is, you know, with traditional practice, with these low numbers of iterations, the design team is really missing a lot of potential. So Ben Welly, I wish I had some results here. If I came down in a few weeks, I may, has been working very hard on developing a similar detailed process for thermal simulation. So in this case, we're starting with digital project, going through IFC, going into Radiance, going into Energy Plus, and then going through our optimizer in a HPC environment. You need to stay tuned for that one. But this is the type of results we're hoping to get back. In this case, we're working with the General Services Administration, where we can help them understand, by looking at these large solution spaces, help them prioritize, for example, which energy efficiency measures to take, and it's going to obviously depend on the building and the region type and things like that. So providing these spaces, these solution space views that help them make good strategic decisions. Okay, so we've found a way to document and communicate design processes to a bunch of people. We found a way to transform requirements into parametric solution spaces. We found with Pydo a way to connect those to analyses and to understand the performance of these solution spaces. Now we need to make some decisions. And it's not always just about first cost versus life cycle cost. It has to do with things like beauty, connectivity, all the other stuff that you want to have going on in a building. So that's what this next project is about. MacDaddy, or multi-attribute, that's many goals, collaborative, many people, design, assessment, and decision integration. What, we came in here a little late, but what time should I, time do these guys need to go?
More time do you need?
I could use about 5 more minutes. Okay. So, problem here is that owners want it all. So this is a slide from Stanford University's facilities planning. And they say, hey, this is what we do. You know, we need to be balancing all of these things in our decision making. So then you go into there, you're like, wait, that sounds great. That's sustainability, right? In my mind anyway, sustainability is about finding the best solution that integrates all these different criteria that we need to live happy, healthy, and economically. So that's what we're after. If you go into their project delivery process, this is the first diagram you come across. Essentially, you're going through scoping, feasibility, programming, schematic design, design development. And they take you through this process of budget control, approval from the Board of Trustees, benchmarking, budget control, benchmark. Problem here is, you know, okay, I see cost in their control. Where's all the other stuff? How does that get controlled? Anybody who went to the AGC thing last night? Anybody? A few of you? Remember one guy said if you control what you measure? So here, they're measuring costs. They're going to control cost. They're going to end up with something that's cheap. What about all the other stuff? So this is a bit of a framework we developed to just go into a particular process. A typical good decision has managers who set up the decision, stakeholders who are impacted by the decision, designers who can generate and assess alternatives, and gatekeepers who can constrain the decision. Each of these people can produce some information, objectives, options, constraints, and analyses. When we look at the project documentation for, in this case, this was one project, we find that it was very easy to understand who the designers were and what the alternatives were that they were looking at. All this other information is communicated much less clearly. It's sort of all in the mind, the conversation. It's not being documented. It's not being managed for. So MacDaddy is a process of building 6 integrated models. Notice the directed notion of the arrows. But again, it's meant to be very iterative. As you get down and you start to understand, you come back and you change your models. Essentially, we're going to build a model of the teams. Those teams are going to help us build models of the objectives, and they're going to help us build models of the alternatives. We're then going to weight those objectives. We're going to analyze the impacts of those alternatives explicitly with respect to all those alternatives, and then we're going to go through some sort of value assessment. So there's a tool, macdaddy.com. I encourage you to go on, check it out, use it for your classes. Essentially, the first step is to develop your teams. So here we're looking at our stakeholders, the gatekeepers, the designers, and the decision makers. And we break down our stakeholders in terms of the different folks who can be impacted by the design. So for example, GSB faculty, we have 3 representatives of the GSB faculty here. Then we go about defining our goals and our constraints. So here are our goals, and you can see at a high level we want to promote academic excellence, sustain environment and community, and be economically responsible. This is kind of your triple E of sustainability, right? Environment, economy, equity. And then we start to break this down and really try to get specific and define what we mean by each of these. So in terms of inspire, we get down to things like be beautiful. Kind of tough to assign a metric to that. We want to make sure it's still in the framework, so we're thinking about it and we're measuring designs against it. Other things like minimize net energy use, we can start to get into some more specific metrics about what we mean by what would be a good and a bad solution for minimizing net energy use. So we go through this exercise of being very explicit about what it is we're trying to achieve. I don't show constraints there, but we also assign constraints. The next step is a preference model. So then each user gets a view which allows them to establish their priorities over these different goals. These happen to be my priorities, fairly well distributed over all the goals. Excuse me, other stakeholders will really focus their priorities in a few areas. They get 100 points to establish these priorities. And then we can look at the overall objectives of the project. So this project seems to be really about promoting academic excellence and sustaining environment and community. And economics is sort of fall where it may, according to these stakeholders. May not believe that, but that's the way this data is showing out. And then we could start to drill in and do some comparison to say, okay, for these two particular stakeholders, this is how their preferences play out. You know, they're kind of in agreement about maybe some, but there's some disagreement about other goals that they really care about, where Helen thinks it's really important to exhibit environmental sustainability, whereas Sandra isn't so concerned about that. Next step is to elaborate on our alternatives. Here's just an image of it. We can attach a BIM model or whatever to actually talk about exactly what that alternative is. Next step is the measurement of the impacts. If you remember back on the goals, I established this 3 to -3 rating for each of these goals to help us measure. Here we're taking each of the alternatives and measuring them in terms of those objectives. And finally, we have value. So we calculate value in this case by combining preference and impact. How much do you care about the goal times how well does the goal perform? If you really, really care about it and it performs really, really well, you get a very high value score. If you really, really care about it, it performs really, really poorly, you get a very large negative value score. If you don't care about it at all, performs really well, you get no value. It's the general idea. So here we can see overall that in this case the concrete shear wall design seems to be winning, and then we can drill into detail and understand why that is. What are the real value adding parts of that particular alternative that lead to its success or failure. I think I'm going to stop there. What I'll do is I'm going to zoom this one. And I'll stop on this guy. And that's essentially what we're trying to do now is we have a number of these different methodologies, and it's about bringing them together to synthesize a very fast design and decision-making process. So in this case, we ran an afternoon charrette where we walked people through from the very beginning of defining teams and objectives all the way through to setting up a parametric model, running it through some analyses, describing our processes, communicating the decision-making metrics about the pluses and minuses of the different alternatives. We find that we can be this explicit about rationale. We can really structure the design and decision-making process and communication to get people from beginning to end very quickly and to support this kind of iteration that's going to help us search and find more sustainable solutions. So I'll stop there.
Do we have questions for John? Yes.
How do you integrate water sustainability design in your design concept?
Great question. I would start with, if you think about this MacDaddy framework, in terms of teams, I'd make sure there's someone in there who's an expert on water. Then we'd get to objectives. We'd work with them and anybody else who had opinions about water to develop specific objectives around water for your design. Then, as we start to generate alternatives, we want to generate the alternatives with water in mind, I guess. We'll analyze them in the MacDaddy impacts in terms of how well the alternatives are performing, and then we'd understand the value of water versus, say, energy and beauty and comfort and all of those issues. This PIDO, the automated analysis, haven't really even thought about that yet. But I'm sure if there are analysis tools which can analyze alternatives for water consumption, then we could integrate that into the PIDO framework. Yeah.
Any more questions for John?
How reliable do you think the commercial energy analysis tools are that you can take on?
Yeah, I'm not touching that. So my assumption is that they're reliable. There's certainly other research going on that's trying to benchmark these and understand how reliable they are. I'm kind of taking my starting point is that we're going to get there. They're going to be reliable. One of the biggest issues from what I can see so far is not so much the physics of them. It's the inputs. It's understanding how to put in good inputs, how to get outputs, and then how to interpret that, and understanding what's included and not included in your analysis. We run into lots of situations where people are running energy model, the building performs much worse than it did, but you go back and you look at the occupancy assumptions of what they thought was going to go into the building versus how people are actually using the building, and they're night and day. And so that's not really the energy model's fault. It's either the energy modeler's fault or the user's fault, or somewhere in between. Yep.
Is it a big workload for you to collect the preference from different stakeholders?
That's
and what if the objective or alternative is changing and the customer name is changing, so they have to input their preference according to that change?
Yes. Okay. Those are great questions. So we handle it on a few levels. One, in the MAC data, you can sort of be a proxy for those stakeholders as a first step. You could say, well, okay, I don't really want to go talk to that faculty member just yet, but I know they're going to care about their view onto the quad and that everything is covered in wood or something. So you can start to put those preferences in early and not have any cost to them in terms of gathering their preferences. So that could be a first step in using the MacDaddy model, is just allow yourself to put yourself in their shoes and model the preferences. In that case, it's really, really fast. And we have little sliders. You can, even if there are 30 objectives, you can model their preferences in 15 seconds if you think you know what they are. Then the next step would be to send the link to them and ask them to do it. So then that's, explaining them what's going on, a little bit of work. Might take them a little longer to figure it out, 5 or 10 minutes. But then, and your second part of the question really touches on this, do people really know what their preferences are, and are they changing? So the changing, we can kind of handle that. Okay, go back anytime you want, change your preferences, and that'll propagate through the system, and we'll see what the impact of value is. There are some methods which are really interesting, which are outside of this now, but which should be added eventually, which are more systematic methods of eliciting preferences from people. So I guess, workshops and things like that, which can really help people understand, oh yeah, I guess I really do care more about water than energy, Does that make sense?
Yeah.
It's a good question.
Well, I think we have to close the seminar in the interest of time, but before we do that, I think we should thank very much John, thank you very much.
Thank you. I'm around for more questions if you like.